Since the beginning of powered flight, knowledge of fuel and fuel systems has been essential. Every aircraft, regardless of vintage, has had some form of fuel quantity indicator. It can be a very simple device, such as this one, a wire sticking up out of the cap on the fuel tank. The cork attached to the wire floats on the surface of the fuel. The height of the wire shows you how much fuel you have in the tank. We've come a long way. There are precise fuel system displays that indicate the current fuel consumption rate, the quantity consumed since engine startup, the quantity remaining, time remaining, plus other helpful information. But the responsibility for managing the fuel is still the pilot's, yours. You must have proper fuel, uncontaminated, and with sufficient quantity to avoid fuel starvation or exhaustion. If that sounds basic, it is, but it's vital to your safety. So let's see what's involved in basic fuel management. Active fuel management is required throughout all phases of flight. Let's review what we know about aviation fuels. Avgas grades have been reduced to a few: red, 80 octane, green, 100 octane, and blue, 100 octane low lead. Jet fuel is either clear or straw-colored. Autogas may be used in aircraft that have been authorized by STC. Any mixture of jet fuel and avgas is absolutely unacceptable for reciprocating engines, simply because the engine will be destroyed by the action of the mixed fuel through detonation. That's why it's important for you to be sure you're getting the right fuel every time you refill. Mechanical safeguards help prevent misfueling. One is a restrictor ring attached to the tank opening. It is smaller than most jet fuel nozzles, making misfueling virtually impossible. Also, most jet fuel nozzles are shaped to prevent their insertion into avgas openings. The pilot's operating handbook depicts your aircraft's fuel system. Many older single-engine aircraft had a single tank. Now, most aircraft have two tanks, left and right. Some systems include main and auxiliary tanks. All systems are equipped with a control valve, on-off on single-tank systems, and a selector valve in multiple tank installations. The system's fuel lines, strainers, filters, and low-point drains all play a part in transporting the fuel to the engine. Your handbook shows you where they all are, which you must know. A vent system on each tank allows air to enter the space vacated by consumed fuel. The fuel in some high-wing aircraft flows by gravity to the engine. On low-wing aircraft, engine-driven pumps keep fuel flowing to the engine. There may also be boost or auxiliary pumps operated electrically. The pressure of the flowing fuel is indicated by one or more pressure gauges that show you how the pumping system is operating. So much for fuel systems for now. Let's look at fuel management. It begins before you go to the aircraft, when you are planning a flight. Your primary consideration is determining the fuel requirement for the flight. Start by determining the distances to your destination. Take into account whether the route will be straight or circuitous, as around MOAs, restricted areas, TCAs, or ARSAs. Your fuel consumption records now come into play. If you don't have the figures, use the pilot's operating handbook or information manual. Know your planned true airspeed. Of course, take into account the forecast wind for your cruising altitude. You may also have to consider the endurance limits of your passengers, which may be shorter than your aircraft's fuel range. Pick a few checkpoints along the route and estimate the ETA to each one so that as you come to it, you can calculate how goes it with the fuel. Smart pilots always pick alternate destinations with enough reserve fuel. How much fuel? FAA daytime VFR requires that there be enough fuel to fly to your first planned point of landing and for 30 minutes thereafter at normal cruise airspeed. Nighttime VFR requires that you have 45 minutes of reserve fuel at normal cruise speed after the first point of intended landing. These margins are really minimums, and you should allow more. IFR fuel requirements are very specific in the regulations. Fuel management continues during pre-flight. When approaching the aircraft, it's a good habit to look for signs of fuel leaks. Leaking tank drains are obvious. Spots on the apron indicate drains that have been leaking. Integral fuel tanks built into the structure may weep through rivets or lines of rivets. Fuel tank caps may lead to entry of water into a tank or to fuel siphoning. If fuel is siphoned during flight, it will leave a telltale trail on the wing. Loose caps, deteriorated seals, or O-rings are the culprits. During pre-flight, checks of the fuel supply begin with the fuel gauge indications. They may give you some idea of the quantity aboard the aircraft, but it must be verified. Visually check the actual quantity in each tank. Some tanks have a visual tab indicator for accurate reduced quantities. High-wing aircraft call for a height booster to enable you to look into the tank. It may be necessary for you to defuel to stay within certain gross weight limitations. Checks of the fuel include taking samples from all sumps. Your handbook shows you where they are. Don't miss any. First, check the color and general appearance of the sample. The color may be right for your aircraft, but the sample may contain water. A sample may be entirely water. Pour it out onto the ramp surface. Water tends to stay on the surface in bubbles. Small quantities of water are easily distinguishable from avgas in the sampler. When poured out, the avgas rapidly spreads out and the water will form small bubbles or drops. Drain until there is nothing but clear avgas. You may have to drain as much as a gallon or two. And it may be necessary to shake the wings to move the water to the drain points. The water can enter the tank as rain or melting snow leaking around an improperly secured tank cap or past deteriorated cap seals. In addition, a partially filled tank may have water form inside the tank through condensation. If there is jet fuel contamination, a mixture of 10% jet fuel with avgas still looks like avgas, but you may smell jet fuel, and the mixture will be slippery to the touch. Suspected jet fuel contamination can be confirmed or ruled out by conducting a simple evaporation test. Put a drop of the sample on a piece of paper. If it contains jet fuel, as little as 5%, the jet fuel will form a halo or ring and will still be visible after the avgas evaporates. If the sample is all avgas, it will evaporate and disappear quickly. Check the tank vents for obstructions that would inhibit or prevent air from entering the tanks. The fuel flow could be affected. Full tanks heated by the sun may cause an overflow through the vent. If there are solid contaminants in the fuel, they will show. Their source must be found to avert plugging of fuel screens. If there is any question, consult a mechanic. So much for the pre-flight phase of fuel management. The flight phase begins before starting the engine. Check the operation of the electric fuel pump as required by the operating handbook. The pressure gauge indicates proper operation of the boost pump. Use the primer for starting as recommended by the airframe manufacturer. Be sure to lock the primer and check it to make sure. If unlocked, it would allow extra fuel to enter the cylinders through the primer lines, thereby causing a rich mixture and a possible loss of power. After the startup, or during taxi, unless the pilot's operating handbook advises against it for your aircraft, switch tanks to check the operation of the second tank. During the run-up and for takeoff, leave the tank selector on the last tank selected to assure a constant fuel feed. The handbook may call for operating the auxiliary or boost pump as a safeguard against possible failure of the engine-driven pump. Always record the takeoff time. Near sea level, normal procedure for takeoff would be for a full rich mixture for maximum available power of your engine. At high density altitudes, generally above 3,000 to 5,000 feet, the normally aspirated engine will produce significantly less than full power. Follow your handbook instructions. What does this altitude business have to do with fuel management? Simply this. As an aircraft climbs to higher altitudes with a set throttle, the volume of air entering the engine to mix with the fuel remains constant. That is, the same amount of air is always entering the engine regardless of altitude. However, the density of the air, that is, its weight per unit volume, decreases with the height or altitude. This means that the weight of air entering the engine at altitude weighs less than at sea level. With less air, the mixture becomes richer, altering the fuel-to-air ratio. This ratio is very important. For reciprocating engines, the useful range of fuel-to-air ratio lies between 1 pound of fuel to 11 pounds of air and 1 pound of fuel to 16 pounds of air. With 1 pound of fuel, less than 11 pounds of air results in a mixture that is excessive in fuel, one that is too rich. Conversely, more than 16 pounds of air results in a mixture without sufficient fuel, a mixture that is too lean. Too lean or too rich will result in a rough-running engine with degraded performance. At the extreme limits, combustion will not occur. You, the pilot, must match the fuel to the weight of air available to create a mixture that is proper for combustion. You adjust or lean the fuel flow to achieve the required fuel-to-air ratio. During a climb, in accordance with the POH, lean as required for smooth engine operation. You can feel and hear the effect of proper leaning. The old admonition of never leaning below 5,000 feet is no longer valid. Lean whenever your power setting is 75% or less at any altitude. For a simple fixed-pitch propeller aircraft, use the tachometer. When straight and level, set the power desired, and increase the throttle friction so it won't creep. Now, lean the mixture gradually, and watch the tach reading rise to a peak. During the process, be sure to maintain a watch outside for other aircraft. At peak RPM, the engine is operating within the maximum power range. Continuing to lean the mixture will cause the RPM to fall off and the engine to run rough. You can feel it and see it. Now, enrich the mixture sufficiently to obtain a smoothly firing engine. While this tachometer method will work fine for a fixed pitch prop, mixture setting for all engine prop combinations will benefit from an exhaust gas temperature indicator, or EGT. The indicator operates from a temperature probe in the exhaust system. If a single probe is used, it measures the temperature of the exhaust gas either from the leanest cylinder or from the cluster of cylinders on one side of the engine. Multiple probe systems have a sensor for each cylinder, located in the exhaust riser just beyond the cylinder exhaust port. No matter which system is used, the peak temperature is the key to the EGT method of mixture control. If we start in the rich area of our fuel-air diagram and lean the mixture, the exhaust gas temperature will rise, peak, and then fall. The mixture ratio at the peak point is when all the air and all the fuel are consumed. Maximum range is achieved at this point. By enriching the mixture approximately 50 to 100 degrees Fahrenheit, we obtain maximum power. This results in maximum airspeed at the power setting selected. The excess fuel in the enriched mixture also gives cooler cylinder head temperatures and compensates for uneven mixture distribution. It is of absolute importance that the pilot's operating handbook instructions for leaning be followed. There are different instructions for different engine airframe combinations. Fuel distribution in fuel injection engines is superior to that in carbureted engines because the fuel is injected directly into each cylinder. Engine instrumentation for injection systems usually includes a fuel flow gauge. Many such gauges are actually pressure gauges calibrated to indicate fuel flow. One segment shows fuel flow for takeoff and climb power at different altitudes, while the other segment shows approximate fuel flow in the various cruise power ranges. The pilot's operating handbook will give specific manifold pressure and RPM settings accomplished through the throttle and prop controls. The handbook will also give appropriate fuel flows for each setting. The mixture control directly controls fuel flow. Some installations have digital indicators reading actual fuel flow. They operate from transducers in the fuel line. Aircraft engines, for the most part, are air-cooled. Engine manufacturers have specific cylinder head temperature, or CHT, limits, which must be adhered to. Again, the POH for your aircraft will detail the limits. One available system measures both EGT and CHT temperatures for each cylinder in the engine. When leaning with this unit, you can always observe the peak for the leanest cylinder, then enrich. An alarm will warn of any change. Frequent monitoring of the fuel consumption is essential to staying on top of the fuel situation. Switch tanks in a given time increment, such as every hour or half hour. It is important to make frequent comparisons of actual fuel consumption with your planned estimates. It just doesn't make sense to fly over refueling points if the headwind is stronger than forecast or fuel consumption rate is higher than planned. With a carbureted engine and a fixed-pitch propeller, any unexplained drop in RPM or in the manifold pressure with a controllable prop may be an indication of carburetor ice. To get rid of it, apply carburetor heat full. At first, the engine may feel rougher because of the ingested water, but keep the heat on until the engine smooths out. Then, readjust the mixture. Since heated air is less dense and causes an enriched mixture, slight leaning may be required. Know your POH procedures. Fuel management is just as important when descending and landing as in other phases of the flight. When nearing your destination, check your fuel quantity and check to see that the selector is set to the tank that is fullest. Start your descent far enough away to avoid any need for a high-speed, low-power approach or unnecessary circling. Low power or power off can quickly bring on thermal shock to the engine and subsequent damage. Keep your airspeed in the green arc range, not in the yellow range or near the red line. Don't go automatically to full rich during descent. Do it slowly to pattern altitude. Keep the engine running smoothly. At pattern altitude, go to full rich, or if at high density altitudes, to the setting that will allow maximum power in case you have to make a go-around. Fuel management isn't finished yet. Taxi with about 1,000 RPM to minimize plug fouling at too low an idling speed. Use the mixture control to shut down the engine idle cutoff. Be sure to set all switches off: ignition, radios, and battery. It's a good idea to check the tank areas for possible signs of leakage that you couldn't see in flight. This is a good time to consider topping off, which helps prevent condensation in the tanks. Be sure you're getting the correct fuel. See that the caps are put on properly to prevent entrance of any contamination. Turbocharged aircraft call for special procedures for fuel management. For takeoff at all altitudes, unless otherwise directed by the operating handbook, always use full rich mixture. Be alert for manifold pressure overshoots, especially during cold weather or on the first flight of the day, and monitor the fuel flow as set forth in the POH. Be sure the proper fuel flow is achieved, as lean mixtures quickly cause detonation in turbocharged engines. If there are any signs of engine roughness or sluggish acceleration, discontinue the takeoff. With a turbocharged aircraft, you must take special care to follow the manufacturer's instructions. They differ for various combinations of engine and turbocharger. After landing, allow a cool-down period for the exhaust turbines in the turbocharger. Aircraft fuel management may sound complicated, but actually it isn't. Just remember these key points. Know the pilot's operating handbook for your aircraft and where to look in it for information. Estimate accurately the quantity of fuel you'll need to complete a flight safely, including reserves. Inspect samples of the fuel from all drain points. Check the electric fuel pump and the fuel feed from all tanks before takeoff. Adjust the mixture and readjust whenever changing power setting to keep the engine operating properly. Review how goes it at each pre-planned checkpoint. It's far better to stop en route to refuel rather than risk running out of fuel short of your destination. Good fuel management is essential to safe flying.